Welcome to episode 301 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm all right, Rob. How are you doing?
Doing okay. Don't think I have any news to share or anything. How about you?
Nothing at the moment, although I guess we passed 6 years doing this now. Because I got a bunch of LinkedIn comments from people. Congratulations on your work anniversary. And I'm like, what are you talking about?
Yeah, that sounds right. I mean, we started in like February, or at least the very first episode was in February, which was just me and John.
Yeah, I didn't join you until May, something like
April
that.
or May. Yeah. But yeah, 6 years going strong, and we're now past another big round number.
Yeah.
Okay.
Numbers are meaningless. It's fine.
They are. I mean, the number's not even visible. The number's for our internal tracking, really.
Right.
Okay. Well, at the top of every episode, I like to read a piece of feedback. This week, we got a comment on YouTube. This is from Aaron saying, "Hey guys, just wanted to say thanks for producing such high quality content so consistently. I've learned so much about C++ over the years of listening. Hope to do an empty crate training course one day." And yeah, well, thanks for listening. And I'm glad the content is appreciated.
That would be fun. I don't know when I'll next be offering a class that random people can sign up for. We'll see.
You're starting to do more training now that the pandemic is
I'm starting to
plan
training.
Plan more training. Okay.
There's nothing that is definite yet, but it looks possible that we may be at some upcoming conferences that are meeting in person, and potentially some on-site corporate kind of classes will be coming up.
Okay. Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today first is Todd Gamblin. Todd is a computer scientist in the Advanced Technology Office in Livermore Computing at Lawrence Livermore National Laboratory. He created Spac, a popular open source package manager aimed at HPC, which has a rapidly growing worldwide community of contributors. He also leads the packaging technologies area of US Exascale computing project and build, an LLNL strategic research initiative on software integration and dependencies. His research interests include dependency management, software engineering, parallel computing, performance measurement, and performance analysis. Todd has been at LLNL since 2008. And also Greg Becker. Greg is a computer scientist in the tool development group in Livermore Computing at Lawrence Livermore National Laboratory. His focus is on bridging the gap between research and production software at LLNL. His work in software productization has led him to work on Spac, an open source package manager for high performance computing with users and contributors all over the world. Greg also works on the Build research project, working to resolve dependency integration issues related to binary interfaces and on internal LLNL infrastructure using Spac. He's been at LLNL since 2015. Welcome both to the show.
You're muted, Todd.
Thanks.
So, can one of you tell me what exascale means?
So exascale it refers to exaflops. So in supercomputing, we measure everything in flops, so floating point operations per second. And exaflop is 10 to the 18 flops. And so the supercomputing generations tend to go in these multiples of 1,000. So before exascale, there was petascale, and there was terascale before that. And those are the milestones, and those are the things around which the funding sort of revolves. We basically, there's an argument made to Congress every 1000x performance that we need funding to continue to get the performance to this level to support, all the physics simulations that we do at Livermore and so on. And so, I mean, that's what the is. It's designed to build a robust software ecosystem for exascale computing. And so that includes,
are you at exascale now?
No. So it's aimed at machines that are going to start hitting the floor late this year, early next year. And it's been going on for a few years now. And so Frontier at Oak Ridge, Aurora at Argonne, and then El Capitan at Livermore are the three machines that are those are the US exascale machines. And maybe someone else will come out with an exascale machine in the meantime, or before or after ours too. But we're hoping to hit it first.
So now I'm just going off rails here, but as soon as you actually hit Exascale, are you going to change the name of your department or the project so that it's whatever's after Exascale, since you're always pushing for that next 1,000 times?
I mean, that has happened, right? Like a lot of research grants before we were shooting for Exascale, we're shooting for Petascale. And
right.
So, those culminated with, to some extent, the Blue Gene, let's see, the Sierra system that we currently have on the floor at Livermore, which is a big Power 9 Volta system. And then before that, our computing facility used to be called the Terrascale Computing Facility at Livermore. And it's been renamed to, I think, the Livermore Computing Complex, because the name sounded slower and slower over time. So, yeah, these things happen in HPC.
So what's after Exascale?
Yeah, I was thinking the same thing.
Zetascale.
Okay.
Zeta?
Zetascale is next.
Yep.
I'd say the US Exascale project in particular is like a limited duration project. So that funding will be going back to kind of general HPC research instead of that particular form of project going on to Zetascale. Might be reconvened later to get there, but it won't go straight through.
Okay.
All right. Well, Todd and Greg, we got some news articles to talk about, so feel free to comment on any of these, and then we'll start talking more about Spac and some of the other things we're working at LLNL, okay?
Sounds good.
All right. So this first one we have is Poxy, and this is a library on GitHub, and I think it's one of these ones we've talked about so many of the libraries from this particular author, I believe. Right, Jason? Looked familiar to me. But Poxy is a documentation generator for C++ based on Doxygen, and it looks like it's just a little prettier than default Doxygen is. Clean some things up, and you can take a look at what some of the output looks like on a link to the Tumul++ documentation, which is another project from this author. And the docs looked really nice. They have a really nice dynamic search function. So definitely worth checking out if you're already using Doxygen. I think it would be pretty easy to switch over to using this.
I've always heard it Tumul.
It could be, yeah.
I have no idea. I'm not going to weigh in an opinion here. Although I agree, can be like a bit of a pain to get Doxygen set up nice. So to have something that gives you a nice, good, clean template to start from sounds good. And I also like there's a nice trutch if you go to the Tumul++ website, that all these docs built with their flavor of their Doxygen front end here have there we go. Yeah, the examples have a highlighted link here. Try this code on Compiler Explorer, and it takes you straight over to Compiler Explorer link where you can actually play with the examples.
Very nice. Okay, next thing we have is a blog post on Red Hat's developer blog, and this is Mostly Harmless, an account of pseudo-normal floating point numbers. And this refers to an interesting set of errors they had where isNaN would not work correctly with some like malformed doubles. Is that right, Jason?
That's how I read it, yeah.
Yeah.
80-bit Intel floating point representation.
It's definitely a little scary because isNaN is something you would call to make sure you have something valid, and if that itself can choke on a malformed double, you're in a bad situation.
Is this the kind of thing you all have to deal with? Floating point representations with all of your fancy exaflops?
Yeah. There's a lot of research going into non-standard floating point in terms of trying to eke a little bit more performance out of the system, especially with AI workflows and machine learning using a lot of like single and even half precision. And so that's what's becoming cheap in terms of hardware, because that's where the demand is. So then there's a lot of research going into how can we take our double precision algorithms and run them at 4x speed on half precision floats and things like that, and can we get similar correctness with that performance boost?
Todd, you're muted
Todd,
again.
you're muted again.
Sorry. There's also some really long-term research on non-standard floating point representations like unums and posits. So non-IEEE, which have better error properties for some stuff.
Okay. Yeah, because I'm just thinking like half precision or something like what 16-bit floating point numbers. If you're doing all these fancy calculus physics simulations, like how do you get a reasonable answer back with that? But you said it's an area of research.
Livermore has a whole bunch of applied math people who specialize in that kind of stuff. It's like way beyond beyond my expertise. But I mean, there's a whole solver team. There's people who work on finite element methods, and basically all the numerical scientists are well steeped in the ways of floating point errors and limiting them.
And I think partially you take a little bit of domain knowledge and you say, okay, this is the part of our calculation that's really sensitive, and this part isn't so sensitive, and maybe we can get a performance boost on the part that's not so sensitive.
Okay, interesting.
Yeah, there have been people who've done dynamic analysis to try to find parts of the program where, for a given run, certain calculations are not, the error is not significant enough that you would need a double precision floating point number. And I mean, most of that is targeted at GPUs where half precision floating point goes way, way faster than double precision. And so we can get a pretty big speed boost, like 3x for going half precision. It also limits your, if you can rework your data structures to use smaller floating point numbers, it limits your, it reduces the memory bandwidth required for the calculation because you're not transferring as much data.
Right.
And so if that's your bottleneck, you can make your algorithm faster that way too.
So are either of you or any of the people that you know at LLNL involved in any of these standard committee things to try to get 16-bit floating point into the standard?
I don't think that's been our focus. I mean, we send people to the standard committee. So you may know Tom Skoglund. He's from Livermore. He's been to a few standard committee meetings, and I guess Chris Earle used to go. We send some people, but I don't think 16-bit floating point's been a focus for us because most of our physics calculations are still using, double precision for now. I think a lot of these are still in the research phase.
Interesting. Okay, and then last blog post we have is on Arthur O'Dwyer's blog, and this is removing an empty base class can break ABI. And obviously, we've been talking about this subject a lot lately, and this is pointing out how, with some changes in C++ 14, I believe, you could take out base classes that no longer are necessary, but the compiler implementers actually can't because it would break the ABI, right, Jason?
Well, yeah, and even more to the point, to me, it's less interesting that removing them would break ABI in a way, or removing them as base classes, because unary function and binary function not only are no longer necessary, they were removed in C++ 17. A conforming C++ 17 compiler shouldn't even have those types,
right? But
they still have them as base classes for things like stud plus so that they don't break ABI.
Yeah.
This is a common theme.
Greg, I noticed in your bio, there was a mention of dependency integration issues related to binary interfaces. Is this a subject you deal with a lot, ABI compatibility?
Yeah, so we started last year, I guess. Todd can correct me.
The fall.
Todd's actually the PI on the project. This research project on binary dependency management, and the idea was that, like, we both work on Spac a lot, and we see the version constraints that users give to their package manager, and someone has to write it by hand, and hopefully they use semver, and that makes it a little easier. But really, we as developers generally don't have a great understanding of our own application's binary interface, let alone anyone else's that we're trying to integrate with. And so if we can go in and actually look at the binary interface, use something like Red Hat's libabigail, get the symbols, see which symbols are actually accessible from the functions that we're interested in, then if our dependency bumps a version and we know actually this version only changed types that we don't touch, well, then we don't have to be too worried about a conflict there. But if they release a patch version, but it changes a type that we touch, we might have to treat that like a major version upgrade in terms of dependency compatibility.
So then sorry, Todd.
Yeah. So the goal is to really take that kind of information and integrate it with the dependency solvers and package managers so that we're not using constraints from humans to figure out if two libraries are compatible. We're actually using the ground truth from the binary. That's the sort of long-term goal for the project.
So then are you in the situation where if you do detect or are made aware of one of these breaking binary compatibilities that you can rebuild world and redeploy when necessary?
Yeah, we usually are, with the exception of some vendor libraries on the machine. So, a lot of people like to use the host MPI or some host math libraries. And so we don't typically rebuild those. But for the most part, HPC stuff is open source, or at least open to you while you're working on it. Like for the export controlled codes and stuff, you have the code if you're on the project. So we deploy stuff from source. And so, yeah, we rebuild everything, but it takes a while. Nobody likes that. They'd like to be able to develop quickly, and we'd like to be able to reuse binaries on the system more easily. Because right now we do kind of rebuild the world, and one of our complaints is like, why is Spac building Perl, or why is Spac building this other thing? And it's for reproducibility. Right. So like system Perls are not all created equal. Some of them lack certain modules, and if you rely on them for your deployment, you're going to break some places. And so, yeah, we rebuild from source a lot, but we want to accelerate it by building from binary. And so we're trying to enable that.
I feel like it would be tempting if I were in either of your positions to fall into the guy who's always in a bad mood role. So that if someone's like, I don't understand why we had to rebuild Perl, it'd be like, do not even get me started on why we had to rebuild Perl. And then just keep walking, like...
We haven't tried that. Yeah, they're usually in a bad mood when they come to us, though. So it's hard. They've got the preemptive bad mood strike going on there, and we try to de-escalate.
we work with a package manager, which means our users work with build systems, so they're always in bad moods to begin with.
Yeah, if you're asking for help on the package manager channel, you've probably been through something.
What does a rebuild world look like to you? Like, is that like hours, days, minutes, months of rebuilding?
It depends on the project. I mean, so Spac does parallel rebuilds. It'll synchronize the DAG bottom up with file system locks, and so you can srun on the single node and rebuild 300 packages in like 90 minutes, like for pretty sizable packages. On a big node.
I'd say
so. It doesn't take that long. But yeah, go ahead, Greg.
It depends what sort of rebuild world we're talking about. Are we talking about someone who has like an application that they care about?
Yep.
Or are we talking about someone who's actually deploying like the system software that they make available to their users? Someone who has an application, if they've got a really complicated application and they're not even building in parallel, we're probably talking 3 or 4 hours of rebuild time. But then you go to a system deployment where they're doing all the compilers, all the MPI implementations, LAPAC, BLAS. They're probably talking, if they do it in parallel, maybe 12 hours to redeploy everything. I think that's what some of the system folks at Oak Ridge who do that have been telling us.
Yeah, they deploy about 1,300 packages for their users. And so their rebuild is like an overnight thing.
It's like building an entire distribution, basically.
Yeah, and that's pretty much what life at an HPC site is like if you're on the facility side. Like you're deploying all the MPI implementations and in libraries that your users use, and combinatorially for different compilers and different MPI implementations, different math libraries, whatever affects ABI. And that can take a long time.
And not just whatever affects ABI, but whatever we think might affect ABI, because like we said earlier, we don't actually have a great detailed understanding of what that is all the time.
Right. Well, at this point, I think it's probably a good idea to actually tell our listeners a little bit more about what Spac is, because that's what you're both here to talk about, and we've mentioned it a few times. So, who wants to go? What is Spac?
I guess I'll go. It's a flexible package manager for building things all the different ways. And so, like if you think about your standard Linux distro package manager, it's for building one version of something and for upgrading it when a new version comes along. And Spac is not that. It's a system for building the versions you want of something, and maybe lots of them. And so we call it combinatorial builds. You can essentially take a matrix of compilers, MPIs, different dependency versions, different flags, different options on the dependencies, and build all of that from source. Or you can cache it as a binary and reinstall it from binary. We do relocatable binaries. But it provides essentially two languages, if you will. There's one for the command line to talk about the parameters you want for the build. So you can say, hey, build HDF5 plus the high-level interface plus the Fortran interface. Or you can say, build boost with streams or without streams. And you can say particular versions or what compiler you want that built with. And then there's a package language. All the package files are basically Python files, but they're parameterized by these things. And so you could think of Spac as a system that takes this sort of abstract spec from the user, makes it concrete into something that you can actually build with all the options set on it, and then uses those package files to instantiate that build. So they're written in a way that you don't have to rewrite the package every time something changes. You want to add anything to that, Greg?
I think that the key thing that then ends up being different about Spac, because of this is our core use case, how do we support that? The key thing that ends up being different is that we're not installing into like a system location. We're installing in user space, and we install into these complex paths that actually include a hash at the end. That's the full provenance of the package and all of its dependencies.
Oh, wow.
So because that hash is different, I can actually have coexisting installs of the exact same configuration of Boost with all of its dependencies the same, except for one dependency I changed the version of way down at the bottom of the tree. And those are going to be separate installs. They're going to live in separate places on my system. And then you can Spac load one of them, Spac unload it, Spac load the other, swap between them.
Okay.
Can we go more into why is that necessary to have all these like different built versions of a library like Boost on your system?
Different applications depend on different versions of Boost. So, we have users who, even in the same workflow, they might use a mesh partitioner that depends on one version of Boost or HDF5 or some other library, and then their application that they want to use in the same environment depends on another one. So you don't always have a software stack that actually is consistent. Different applications can have different versions of things. And the way that we link stuff in Spac, we use RPath. And so basically every install knows where its dependencies live and which ones it built with. And so like one of the core design philosophies is you run the way you built, because basically we see a lot of people screw this up, right? LD library path, people who mess with that, they're in for a lot of pain when they try to deal with something like this. Because it's a global variable in your environment that tells the linker where to find stuff. And if two different programs depend on two different versions of a library, then you're in trouble. So the idea with Spac is that you or the package manager knew what you were doing when you built this thing, and you've probably forgotten that long since when you get around to running it. And so we want to run the way you built.
So if I have three packages that all rely on one specific version of, three applications that all rely on one specific version of Boost.
Yep.
And then a fourth application that uses a different version of Boost, I will have two versions of Boost installed.
Yeah, that's right.
Okay. Yep. I was just trying to think, like, initially I thought you were saying that it would be kind of like, I cannot remember the name of these tools, but where you can like bundle all of your Python stuff into Okay, where it would have everything bundled together for that application, but no, you do have a shared location.
Yeah.
So every package goes in its own prefix
Okay.
when we install it, and the prefix gets a hash that is basically a function of that package's configuration and all of its dependencies configuration. So it's a Merkle hash. It's like a git commit tree, and you share where it's possible, but you can differentiate where it's not.
And then for a single build, Spac install boost, if there are multiple dependency paths to the same package, those are unified. So we use a directed acyclic graph as our internal data structure, and we make sure that each package appears only once in the DAG.
Yep.
Okay.
And that's the idea there, is that your linker only supports one version of a given library in a particular process. And so you can have two programs running with different versions of a library, but at least the way that all C runtimes that I know of right now work, you can only have one version of a library linked with your program unless you want to have nice race cases at runtime, right? And for C++, it's actually an ODR violation to do that. So,
that doesn't stop us.
It does not stop us, and I kind of like that because I'd like to exploit it one day, but we're not there yet.
So I'm trying to then wrap my mind around because Conan does kind of similar things, right? I'm assuming you tried Conan. Okay.
I have a cursory familiarity with Conan.
Right. So you can, if you install a package with whatever specific set of compiler flags and compiler version, whatever, then it makes a hashed installation as well. And then when you go to use Conan, then it says, okay, I want this version. And by the way, this is all the flags that I'm using. And it goes to look to see if you have that installed. And does that sound similar to what you guys are doing? Or
yeah, I looked into this initially. Conan and Spac are similar in a lot of ways. Spac's actually older. It started in 2013, and Conan came along later. But Conan, it seems like if you pick a version on a package, it doesn't do anything to ensure that you're running with what you built with. So you can pretty easily get yourself into an ABI nightmare that way by setting versions on things throughout your stack and forcing them to be a certain thing in the resolver. Whereas with Spac, at least right now, we deploy as if built from source. And so there's this sort of hash structure that we talked about, where you get all the dependencies that you built with, and we don't try to mix that stuff at deployment time. That's actually one of the motivators for this project that we talked about earlier, right? For build, is we'd like to have a little more flexibility in deployment to reuse more binaries, but that means in many cases, potentially violating ABI because you're no longer in a situation where you're deploying as if you built from source.
Right.
So we're trying to add support, and we have some preliminary prototypes for stuff where we would swap in a binary with another ABI, and we keep the provenance for that so that we can go and check the metadata and understand if we did violate ABI somehow when we do that deployment. So we're moving to a model where we could safely reuse binaries, but I don't think we're quite there yet. That's the research project.
Okay, that makes some sense. Yeah, because with Conan, it's a build packaging tool, package manager, but when it goes to deployment, you're on your own. How do I get those binaries, or do I just try to statically link everything or whatever?
Yeah, that's right.
Okay.
Yeah, I'd say the package model is different, and Spac also has. I was looking through, I guess, key differences between Spac and Conan. I'd say Conan has more of a C++ focus, obviously, because we're trying to support a bigger ecosystem. So we're trying to support Fortran and Python and R and all the other things that you would combine with your C++ libraries. The other difference between Spac and Conan is the dependency resolver. So we have recently gutted Spac's concretizer, which is what we call the dependency resolver, and replaced it with a answer set programming solver. And what that looks like is it's Prolog that boils down to SAT on the back end.
Wow.
And so it's kind of cool because you write your dependency resolution rules in first order logic.
Okay.
And users don't see this, so don't get scared.
That's
But
kind of awesome. It's actually like legitimately the first commercial use of Prolog I've ever heard of.
oh no, it's not Prolog, but it's
But you said it's like Prolog that
it
boils
is.
down into SAT solvers, right?
It's a very similar looking language, but it's a
Okay.
little different. It's got some quantifier statements that I don't think are directly analogous to anything in Prolog. For example, that you can say I need at least one and at most one things that look like this.
Right.
And I think the reason we added this is because all of these conditional dependencies in our packages got to be really complicated to manage. Like Spac has a very expressive DSL. You can say that, boost depends on MPI when the MPI option is enabled. And it'll, and MPI is a virtual package in Spac. So you can use any of the MPIs that support the API that you want there. So like you can build boost with MPitch, boost with MBAPitch, boost with OpenMPI. Those are all separate installs, right? And same for, a normal library that's not HPC specific. All of that, conditionality in the solve meant that, our dependency solves were becoming increasingly wrong with our old greedy solver. And so the new one it's pretty awesome to see what the ASP solver can do, because it's essentially doing SAT plus optimization on the back end. So we optimize for like 11 different criteria in the solver to try to pick, recent versions, default values of build options, and so on. And the solver is, it can tweak the options. So if you say, I want this package built with, MPI or with MPitch somehow, it'll figure out that, on that package, I need to flip the MPitch option or the MPI option on so that I can depend on MPitch and get it in the graph. And, there's a lot of cool stuff like that. It'll solve for, if you ask for a particular compiler and it knows that compiler does not support your microarchitecture, it'll, set the microarchitecture to something lower that the compiler can actually generate. So you're sort of simultaneously solving for compiler architecture support and, pick an architecture for a compiler. And it'll warn you if you say like, hey, I have, the GCC 4.x from my distro in my configuration registered, and you try to install something built for Skylake, it'll say, yeah, you can't do that. That compiler does not support Skylake.
So we've spun out a separate project called ArchSpec, which is the detection and compiler support levels for all of the different architectures. So, if you read proc CPU info and you get these flags, it's a Skylake. And if it's a Skylake and you're trying to build for GCC, well, that's supported starting at this version. And in the first two versions that support it, the flag is this, and then it settles in to be -march equals Skylake, things like that. And so it's basically a giant JSON file with all of this information and then a little front end around that to do the detection.
Wow.
And that's something you can use in another tool, because like Greg said, it's just a JSON file. It's got a Python interface on top of it, but you can use that to reason about compatibility. So if you want to tag your binaries with the microarchitecture they were built for, then you can take a binary, look at it, say, oh, this is built for Skylake with AVX512. And you could say, oh, this is not, it's not compatible with my Haswell system because it's going to have instructions that my architecture doesn't support. And that's you've got like a less than and a greater than operator that you can use on these CPU names.
I'm fascinated by Greg's comment that it sounded like you said the tool can actually look at proc CPU info, whatever, and figure out what the ID flags are. On your HPC clusters, are the CPU architectures 100% homogeneous?
That depends a lot on the cluster and on the philosophy of the site that hosts that cluster.
Yep.
Okay.
I'd say at Livermore, we have almost entirely homogeneous clusters. Homogeneous in the CPU architecture. We have heterogeneous clusters where it's CPU, GPU.
Right.
But homogeneous in the CPU architecture.
And that's per cluster.
Yeah,
So,
and
like,
so
it's
this
not-
only comes up
yeah.
when you go between clusters at
Mhm.
our site. But there are other sites that, as they
Like their
get
users
new
less.
nodes, they add those nodes into one sort of large cluster, and they might have separate Slurm queues for the different architectures. But instead of getting 5 new nodes and setting up a little cluster, they just add those to the big cluster they have, and now you've got a heterogeneous cluster. And so we'll see a lot of folks at sites that do that will set things in Spac that say, like, set my default architecture to be Ivy Bridge instead of whatever I happen to be on at the moment.
Right.
And because they know that that is the lowest common denominator of every chip on the system that they're targeting.
There are sites like Fugaku where they have like the compute nodes on the cluster are A64FX, so that's the ARM with SVE, but they have ThunderX2 and x86-64 front end nodes for whatever reason, and that can be somewhat difficult to work with.
I only thought about this because Compiler Explorer, if you do -mark equals native, Compiler Explorer will pop up a warning saying, you don't really know what CPU you're running on because Amazon's clusters.
Well, that's exactly why we wanted ArchSpec, is because previous to this, we were essentially building with March native. And if you want to distribute binaries, and you want them to be optimized, and you use March native, you have no idea where the binary can be used. So that was the motivation for ArchSpec. We want to label it with a microarchitecture, not just x86-64.
Yeah, there's 2 ways to solve this. You can either label them, or you can just build everything for the baseline architecture. And build everything x86-64 works, but it's not really appealing for high performance computing. We want to get everything we can out of these chips.
Right.
Other folks, have you seen the x86 levels that they introduced into recent GCC and Clang?
No, I guess not.
So there's other folks have realized that this is a problem, and they've tried to simplify the optimized builds that you would do. So there's x86-64, which is what you're familiar with. There's V2, which I think is Nehalem-like, V3, which is like Haswell, and V4, which is like Skylake AVX512.
Interesting.
And
V2 is when you add like SSE4, I think.
Yep.
Okay.
V3 is where you add AVX2.
Yeah.
And V4 is where you add AVX512.
And so they're nice because it's kind of like the ARM versions. They're virtual architectures, and you can build for those and get some optimization because the compiler could use all the fast vector instructions. But you're not building for a really, really specific microarchitecture. So we're actually adding those to ArchSpec. Someone contributed that recently. Pretty happy about that.
That's cool. And I guess on these supercomputing clusters, they take a while to spec out, build, and install. So even if it's brand new, it's not necessarily the CPU architecture that came out yesterday, right?
It depends. So like in some cases, we get unit 0 machines. So like for our biggest machines, like the Blue Jean machines, Sierra, and then El Capitan that's coming along, we work with the vendor like 5 years in advance to set up that contract. And then our machine will be, one of the first with a new processor generation. Okay. Yeah. So it really depends on the system. For our commodity clusters, we're targeting something different when we buy them. We're going for price or for optimizing for cost, and so we'll typically choose something that's not the bleeding edge because you get a better price performance that way.
So a few minutes ago, you mentioned how Spac works with other languages like Fortran and R. I think you said. Is that because users of Spac are not really writing C++ programs? They're probably writing something in Python, but it's making use of C++ libraries. Do you want to go into that a little bit?
Sure. Do you want to take it, Greg?
Sure.
Go for it.
So users of Spac are writing everything. Okay. We have Spac users who are writing pure C++ libraries that only depend on other C++ libraries and could use Conan, maybe have a Conan package as well, but have also contributed a package to Spac because they don't know what their users are going to want. We have some folks who exist in kind of a pure ARM ecosystem and they contribute a bunch of R package, a pure R ecosystem, and they contribute a bunch of R packages, and those packages all depend on each other and are fairly self-contained. Some of them have C and C++ components as well. And then the HPC specific thing is you get a lot of these kind of big physics codes that use C, C++, and Fortran all at the same time.
And Python and Lua.
Yeah. And everything else that they can get their hands on, because whatever was best for this particular sub package is what they used, and the build system is a problem to figure out later. And so we've got some of those at Livermore. We've got some of those in the open source community that use Spac, and they kind of have their own challenges. And we think Spac's good at a lot of things, but that's really where our starting use case was in terms of this HPC workflow, where all the languages are thrown in together at once, and that's kind of what has defined what features we need desperately in terms of being able to support, intermixed C and Fortran compilers and things like that.
It's getting good.
I was wondering, along the thought that Greg was talking about, like, do these things play nicely with like other package managers, like pip, for example? Like if I say
you can make a Spac environment, and you can use pip inside of it.
Make a Spac environment.
Yeah, so Spac supports the notion of virtual environments, kind of like what virtualenv would do in Python.
Okay.
We said earlier that you install into separate prefixes, but one kind of cool thing is that you can also say, I have this stack of software, I want to present it to users in a different way. And that can either be, if they're all consistent, you can link them into one prefix, and that's and that becomes a virtual environment. Or you can put them in some nice file system layout that differentiates them by like MPI, compiler, and so on. But yeah, so if you make a Spac environment, it's you write this YAML file that says I need like these 6 Spac packages. You can say Spac install that. It'll spit out a lock file with all the versions that it actually concretized to. But then inside of that, if you want to use pip, you can. We do, to enable that, we do the same kind of tricks that virtualenv does. We copy the Python interpreter in, so it thinks it actually lives there. And everything else is like symlinked out. And then, you can use pip like normal inside the Spac environment to deploy some Python packages on top of what you've got there.
All right, so if I create a Spac, I keep wanting, like, how, first of all, before I get to my actual question, how often do you have jokes or whatever about spackling over the problem or something like that? Because I just keep wanting to. There's a whole thing about to spackle it.
I don't know if we've had that one so much. We have Spactivate and Despactivate for our environments, though.
Okay.
Yeah, and that was done to differentiate between deactivate, which pip has, so you could use both at the same time.
All right, so I create a Spac environment. I install my favorite version of, I don't know, Boost and libformat or something like that.
Yep.
And now I want to compile my C++ project that uses CMake inside of there. Like, what does this look like? Does CMake just find those packages? Because, like, what is...
It does.
So when
you want to take it?
Go ahead.
Yeah.
When we activate the environment, we put all of the paths to the things in the environment in your user environment.
Okay.
And so we have what we call prefix inspections. We look at the package, we see it has a bin directory. Okay, if it has a bin directory, that bin directory gets added to your path. If it has a lib directory, that gets added to your LD library path. And one of the prefix inspections we do is just for the prefix itself, which every package has, and we stick that in CMake prefix path.
Yep.
So CMake's going to go look where all of our packages actually are.
Yeah.
Okay.
We try really hard to make it so that when you activate the environment, that you're going to find all the packages that are in the environment.
That sounds pretty fancy. Yeah. It sounds like if I'm, managing 3 clients at once with my contracting work, that is, this could be helpful. Instead of having 3 virtual machines set up with all of the things, which is how I would have been working for the last 10 years, I could have one and have Spac.
Yeah, and we have support for containerization too. So if you make a Spac environment, you can take that and you can deploy it on bare metal. You can choose whether you want it in one prefix or all separate or whatever.
But
and then you can,
there by bare metal, you do actually mean an operating system. You don't mean like it's not an operating system by itself, or
it is not yet an operating system by itself.
Okay.
It is, yeah. If we got down to libc, we could start thinking about really minimizing the environments and having a self-contained stack. We have not gotten down to that level yet. So Spac is basically stopping at the compilers and runtime libraries.
Okay.
But yeah, you can then call Spac containerize in your environment, and it'll spit out a Docker file that builds you a container that has that same environment in it. And so you can use
that is fancy.
Yeah. So you can use it to have the same environment deployed on bare metal as you might run in the cloud in a container. And the abstract description with the package names is similar, the same. And then the lock file that you get in either of those environments is different.
Huh. So if GCC 12 were to come out tomorrow and it destroys ABI compatibility and breaks all the standard library, you guys are just like, no big deal. We're ready for this. Go ahead, press the button. We can rebuild with GCC 12, even though it broke all the things.
Yeah, and then we'll patch all the packages that stuck W error in there for all the new compiler errors that show up when that happens. But it's, aside from things like that.
That's like a service announcement here, PSA. Don't put W error in your public flags on your projects. That's
Help
please.
a packager.
Yeah.
Help your local package manager stop using W error. We may so one thing Spac does that may be interesting to you guys is we use compiler wrappers internally. And so, the way that we get all the RPAs that we mentioned earlier, so that the libraries know where to find their dependencies in there, is we have wrappers that inject the RPAs and include in libpaths for like your dependencies. So, that's one way that we try to isolate these things. In some ways, like a Spac install in its own build environment, it thinks all the dependencies are just installed on the system, because things like auto tools builds that test for whether they can include a header, they just work. And that's how we let you deploy with different flags. They get injected via the compiler wrappers, and packages can opt out of that and pass them through the build system if they want to, but that's our default. So yeah, I'm very, very tempted to take the compiler wrappers and just start stripping W error out. We could do something like that, and I think that would make things work pretty well.
Is it fair to say that this only works on Linux based off of our conversation now at this point?
It does at the moment, but we are working with Kitware.
It works on Mac OS also.
Yeah, that's true.
Okay, so Unix-like operating systems, I guess.
At the moment, but Windows support is underway, and so Kitware is working on that along with TechX.
Okay,
and they have some preliminary builds of initial packages done. So like gtest built with an unmodified Spac package on Windows with their modifications to Spac. There's a lot of plumbing to rip out, but we're looking at some interesting things. So like one thing that it's cool working with the Kitware folks, because they come up with neat build things because they've seen it all via CMake.
Right.
We talked about this RPath thing, and PE doesn't support RPath on Windows. The executable format just doesn't have it.
Right.
Although you can, and the tooling doesn't support it, but you can have in the format a full path to your dependency library in a Windows binary. And so Brad King came up with a way to hack .lib files on Windows to get something like RPath, so that we can use our tooling to not have this restriction that Windows has, that the libraries basically have to be deployed alongside the executable. If you've experienced that. So we're hoping we can have kind of the same link model when we get Windows support as we do on Linux and Mac OS. Because RPath is super helpful for this kind of stuff. We don't want library hell.
Right.
So we've talked about how Spac is built very specifically for the HPC research community, but it does sound like it could be very useful for kind of more general use case application developers who want a package manager. do you agree? Like, does it make sense for non-HPC, non-research, developers to use
Yep.
Spac?
Yeah.
And
we
are those packages available? Like, lots of other libraries, not necessarily meant for.
I mean, like
yeah.
CalSay is in Spac. Like all sorts of things that are not HPC are in Spac. There's 5,500 packages, and
Oh wow.
Yeah.
We joke that I'm the first native speaker of Spac because I started working on it straight out of undergrad and didn't really have a lot of experience with the Linux package managers. I use Spac as my package manager on my laptop.
Okay.
Yep. Me too.
So you don't even bother using your Pac-Man or whatever.
Yeah,
or
I'm on a Mac, so it would be a Brew,
okay.
but no, I don't have Brew installed. I just and since I work on Spac, if a Spac package doesn't exist for something I want, I just create one and then I keep using Spac instead of having to use another tool.
Yeah, you can just say Spac create URL and it'll examine your tarball or whatever and make a template Spac package for you to hack on. It'll say, oh, this is a CMake package, so I'll make you a CMake boilerplate build, and you can go and write some code to actually execute the CMake and make install. I guess
I was just going to ask how easy it is to make a Spac package if you want to add a new library. It sounds like it's extremely easy.
Well, yeah, I mean, it depends on how complicated your library is, right? If you're making a new Spac package, and luckily you don't have to for TensorFlow, then it is rather complicated, right? Like there's a lot of options, a lot of dependencies to add. You're still responsible for adding your dependencies and setting, version constraints and things like that. So if it's a big package, yeah, it can be complicated. But for something simple to get you started, yeah, I mean, I think you can just say Spac create, give it a URL to the thing, and it'll generate you a recipe.
If you're a developer of a package and you have a good sense of what your dependencies already are, then it's pretty easy. If you're looking at someone else's package and they haven't told you what the dependencies are, then you have to figure that out. But beyond that, it's kind of as easy as their build system makes it. You have to figure out how to pass the options that it needs. If their build system is arcane, maybe you've got a little bit of digging to do to figure out exactly what the options are. But if their build system is reasonable, you just pass the obvious options, and that's it.
And it's been around long enough that we have, some canned support for the common build system. So it gets back to, I don't know if you saw Robert Shoemaker's, the VC package guy, his talk at CppCon about don't write packageable software. Like make sure that your software is using something known, and don't try to do your own thing because it's better for you, because the people installing your software don't understand your bugs. They understand CMake's bugs.
So this can actually, I'm sorry, but I was just browsing through your package database. It looks like if I go to install, if I'm just starting from scratch and I'm going to install libformat, for example, because it's one that I just looked at, which depends on CMake, it will also to install CMake automatically so that it can then...
Yep, it'll go down to the build dependencies.
It really is like a full operating system package manager. It's almost like, a part of me is like, in a way, you reinvented Gen 2 Linux, but
people have said
quite.
that before. Yeah, Gen 2 is single prefix, right? And so it does not have the same kind of multi-versioning that we do. Like they have slots in Gen 2, but it doesn't. It's not the full combinatorial space like Spac is. And so, yeah, Gen 2 is also a full OS, and it goes down to libc. And so that's one distinction, at least for the moment. We'd like.
I was going to say you're not that far off.
Yeah, exactly. Yeah, one of the things we're adding is better support for compilers, and I mean the incompatibilities that we see now in builds with Spac have to do a lot with the runtime libraries underneath compilers. So if you're doing mixed compiler builds, which our code teams do, and you want to build with the Intel compiler for most of your stack, but you have some things that only build with GCC. Getting the runtime libraries to be compatible there, like especially libstd C++, can be pretty complicated. And so we're trying to model that fundamentally in Spac. We want to have libstd C++ in the DAG, and we want to be able to ensure that the libstd C++ that this package used is compatible with the one that this other package used, and they can be linked together. Or ideally just use one and get all the compiler flags correct so that Intel and GCC are using the same one. Or with Clang, this comes up. It can do libstd C++ or libc++.
I am legitimately confused as to why the DOE projects that I've been working on for the last 10 years haven't considered using Spac for our dependencies.
It's getting more uptake. Which ones are you working on?
I've been involved with Energy Plus and OpenStudio off and on for
cool.
10 years now. I'm assuming you're at least familiar with Energy Plus.
Actually, no. So what is that?
It's building energy modeling simulation software.
Oh, neat. Okay.
It's the other part of the Department of Energy that's not involved in nuclear physics.
Okay, that's yeah. So we're mostly with the Office of Science and the NNSA labs, which are all nuclear physics.
Right.
Well, not all. There's a bunch of climate science and other stuff that goes on. I mean, it's a big place.
Right.
Yeah.
Okay.
So I mean, I guess I would say Spac. It's a general package manager, and if you're thinking about how that applies to C++, I would say that like if you have an ABI problem in C++, like people in HPC have probably seen that either in C++ or somewhere else. So like we're solving in some sense a more general problem,
right?
Than what the C++ folks are doing. We have all the same problems. Fortran is worse about ABI than C++. It like even the module files like change compatibility with compiler minor versions sometimes. So it gets pretty nasty. And because we support that, I think it's something for the C++ folks to consider pretty seriously, because C++ apps often aren't just C++. Like, we link in a lot of Fortran, we link in a lot of other stuff, and at some level you get into this interop state where you need something that really thinks about all these packages.
Yeah. Well, we're starting to run out of time, but before we let you go, I'm wondering what else is on your roadmap for the future. You mentioned that Windows support is being worked on. Anything else you want to highlight?
Windows support, better compiler support, the ABI analysis that we're doing under build, and then Greg, you got anything else? Developer features.
Developer features. We want it to be that you can just specify a Git hash, and we'll treat that as a version, and we'll actually pull the Git repo, and we'll look for the versions we know about, and we will figure out where your commit that you specified sits between those versions, so that if you have something in the package that says if it's version 3 or earlier, it needs this flag, and otherwise it needs this other flag. So we need to figure out then whether this random commit that we're building is before or after 3,
right?
To be able to throw the right build system flags, or even maybe use the right build system if you switch to CMake at a certain point.
Yeah.
So that's something that we're working on. Binary bootstrapping for Spac dependencies. The default concretizer in Spac is still the original one, and we have this new one with ASP. But ASP isn't pure Python. We can't just vendor it into our project. And we really like the fact that Spac currently, you can just git clone Spac and then run it. And so we're working on having binaries for built on many Linux, so they'll work on all the operating systems, and built for the base architectures, ARch64, x86 64, PowerPC 64, little endian, that have the binaries for Klingo, which is the ASP solver that we're using. So that we can just automatically grab those binaries when we need them and use the more advanced solver right from the get-go, instead of having to kind of bootstrap it. Well, I guess that would be bootstrapping it, but instead of having to bootstrap it with a source install that requires then concretizing with the old one to get there.
Yeah. And for developers, I mean, right now you can make a Spac environment and say, Spac develop some package in your DAG. It'll check out the source, and you can work on it and build the whole stack with that thing. It'll rebuild the stuff that depends on it if you modify the source. The Git integration Greg was talking about is so that you can just check out an arbitrary version of the thing. We want to make that integration smoother. Right now, it kind of has to be written into the package.
Okay. All right. Well, it was great having you both on the show today. Thank you so much for telling us about Spac. Anything else you want to plug before we let you go?
No, give Spac a try. I mean, and join our Slack. There's over 1,000 people on there, and there's help if you need it. We're also on the CppLang Slack, so there's a Spac channel. It's not too active at the moment, but we'd love to see more C++ people give us a try.
Awesome.
Oh, I need to get on that one.
Yeah.
All right. Thanks, Todd. Thanks, Greg.
All right.
Thank you.
Thanks a lot.
Thanks.